Hi everyone, thank you for joining this Icarus presentation. My name is Ida Bülow Gregersen. I'm working for the consultancy company Ramble, and the topic that we are looking into in this presentation is how to make the case for climate adaptation. So what can you expect from watching this? With this presentation, I am going to give you a method for finding the optimal level of adaptation, a method for choosing between two different adaptation options. Both is shown via an example of which costs and benefits to include in such an analysis. We are also including wider benefits that often are associated with nature-based solutions. And then finally, we also look into how these costs and benefits can be evaluated. The whole presentation is centered around a fictive case, where we have a major highway with 3 lanes. This highway serves as an important connection between 2 large cities. As decision criteria, the NRA have 3 key performance indicators. One is centered around availability, the other is centered around safety, and the final one is centered around having a low maintenance and repair cost for the network. The NRA also have a policy, and that is to show social and environmental awareness. Below on the slide, in the bottom, you can see a table with some descriptive numbers on availability and safety that we will need for later. There is a culvert under the highway carrying the flow from a small river. When we look into the existing guidelines, this NRA have very clear guidelines regarding internal drainage, meaning how to handle the runoff from the water that falls on the road. But the guidelines are quite vague when it comes to external drainage, like this culvert. The culvert was designed around 50 years ago, and when it is evaluated today, it is seen that it has the capacity to handle a 2-year event. But in the future, with a changing climate, we expect much more higher rainfall intensities. And we will expect a situation where the capacity of the culvert will be exceeded quite often. The question then is, what is the impact when the capacity of the culvert is exceeded? Flood simulations are applied for this type of resilience analysis, and they have been done here for a 10-year event, a 25-year event, and a 100-year event. For the 10-year event, the simulations show that you will have water on the roads. 2 out of 3 lanes are affected, and the travel time is increased compared to normal. And after the flooding is finished, you will have to do like a minor check on maintenance to make the road usable again. For that 25-year event, the situation gets even worse. It's all lanes heavily affected, and the travel time is increased by 200%. And once again, when the water is gone, the road needs like a minor check to make sure that it's usable again. If a 100-year event happens, the road is completely closed. You can end up with a situation where the brinks around the road will become unstable, and pieces of the road is breaking off. So afterwards there will be a high cost associated with re-establishing the road. Based on the resilience evaluation that was done on the previous slide, we conclude that the level of resilience is not acceptable. So we do need to change the drainage capacity, but the question is to which level? And by this I mean, at what return period can we actually accept that we have accumulation of water on the road? There are many different adaptation options that can increase the drainage capacity, but the question is which one is optimal. In this example, we look at 2 different options: retention in the form of an NBS and conveyance in form of increasing the size of the culvert. When it comes to choosing adaptation options, there actually is a preceding step that I didn't include in this presentation, but you have to make a screening to assess all the different possible adaptation measures. and the Icarus project has in fact made an Excel-based tool exactly for this purpose. Now we are looking at two different optimization levels, and we are looking at two different strategies to obtain these levels. And the question is, which to choose? We are also introducing a reference scenario that corresponds to a situation with no adaptation. And then we are introducing the large table on the right that we need to fill in to help us in the comparison between the different optimization levels and the two different strategies. Now let's look into the table. First, we compare the two levels against each other. If we choose level number 1, we will improve the availability compared to a situation with no adaptation. If we choose level number 2, corresponding to a very large culvert, we will improve the availability even more because the flooding of the road will be very rare. The table will also help us comparing the two solutions against each other. For example, the NBS solution will give us additional co-benefits that the traditional gray solution does not. Yes, now let's look a bit into the NBS. This solution is a storage basin that will retain the runoff from the catchment and prevent it from flooding the highway. The NBS solution is projected to be in an area that is not accessible by the public today. So building this NBS will also create recreational value, because just giving people access to the site and the whole experience of walking there, that will be an integrated part of the NBS solution. Okay, so now we are looking into the estimation method. First of all, you need flood simulations of water depth and water extent. Then you need to figure out, when there is a given depth of water on the road, how is that going to affect your availability and the safety. You can use traffic models for this, or what you can also do is to look at data from traffic measurements that happened during earlier events. Finally, you also need unit prices for injuries and for delays. With all this information, you can start filling in the table that you see on the upper right. Another thing that goes into this table is numbers on the costs associated with cleaning and repairing of the road. And as you can see from the table, the adaptation solutions will reduce this cost. All of the numbers from the table is summarized, and they go into the adaptation curves that you have below. What you will see from these curves is that you obtain the highest damage cost for large return periods, and that you obtain the highest damage cost in the scenario where you don't have any adaptation. Now on this slide, I'm going to introduce some important terms that will help us take the result even further. The first one is expected annual damage. Damage is associated with a probability. We saw that on the previous slide where we calculated the damage cost associated, for example, with the 100-year event. But the thing is that you don't know when the damaging event will happen, and this is handled by calculating expected annual damages for each year. But what you will see from the curve on the slide is that the expected annual damage is increasing over time. And this is due to climate change that is taken into the calculations here, because we know that climate change is changing the rainfall intensities, and that the 100-year event that we experience today will happen more often in the future. And therefore, in the future, we have higher expected annual damages. We also need to do discounting, because a bill that you receive today is far more important to you than a bill that you receive 10 years from now. And this is of course also valid for the expected annual damages that are calculated, in this example, 50 years into the future. When we do discounting, this will allow us to calculate what we call the net present value, the value of the project seen from today. And this is one number only, and one number for each of the two different levels of adaptation, but compared to the reference scenario of doing no adaptation. If we choose the NBS solution, we also need to monetize the co-benefits that we believe are associated with these types of solution. We believe that there is an additional value created with this retention volume, because we believe that it is going to be an excursion spot for people that live in the two cities nearby, so that they will travel there in the weekends, for example, to go for a walk. In the literature or from the national environmental agencies of your country, you can find recreative values of the green spaces, like I have in this example, and here it depends on the size of the solution. So you take the net present values of the benefits that we estimated on the previous slides, and then for the NBS you add the value obtained from the co-benefits. So you go from the blue line to the blue dotted line. You also need the cost of your solutions. So the cost of increasing the culvert on both levels, the cost of making the retention volume of the NBS on both levels, and into this cost also goes the cost of acquiring the land where the retention volume is supposed to be located. You need to take into account the maintenance costs of both solutions. You need to do discounting, and then in the end you can calculate the net present value of the cost of the two adaptation solutions at the two levels, as is given in the table below and plotted on the figure. Now we need to bring everything together. First we look at the culvert. We have the costs and the benefits calculated for the two different drainage capacities. The cost is the purple curve and the benefits as the blue curve. And you see for drainage capacity number 1, the two curves are pretty close to each other. For drainage capacity number 2, the costs are higher than the benefits, so the net gain of this option is actually negative. Now looking at the NBS, we see that the benefits are the same as for the culvert, that is the blue line, but the NBS solution also gives us co-benefits, that was the blue dotted line. We have the pink line, that's the cost of the two solutions. You subtract the pink line from the blue dotted line, and that will give you the net gain on the green line. And you can see that for both drainage capacities the net gain is positive for the NBS solution, but you obtain the highest net gain by choosing drainage capacity 1. So now we have arrived to the conclusion of the analysis. The optimal solution in this case is making a retention basin in the form of an NBS, and it should be designed to fulfill the demands of drainage capacity 1. We have now reached the summary. So what needs to be in place for you to be able to make the case for adaptation? First of all, the decision criteria. In my case, I used KPI values for safety and availability, and also KPI values for maintenance costs, including repair. I also had, in my case, an NRA that had a policy about social and ecological awareness. When we come to the data that you need to make these assessments, you need numbers on safety and availability for the situation today. You need knowledge on the climate change that is expected. You need to be able to do flood modeling so that you can figure out what is actually the impact of the different types of rainfall events. You need values to put money on delays and injuries. You need values to put money on the recreational space of green. And then you also need discount rates. I really hope that this presentation has inspired you and can help you in the process when you need to make the case for adaptation in your own organization. Thank you very much for watching.